at the end of the lecture so that you can write it down. But if you just remember the guy's name, that's all you've got to do on YouTube. They know who he is. Okay. Okay. I just want to check whether I had anything else now. This is test your understanding. You saw the question yesterday. Let me turn this down a bit. What do you think the answer to the first question is? Is it A, B, or C? Who thinks it's A? Okay, who thinks it's B? Okay, who thinks it's C? No, the answer is B. And here's the opposite question. I'll give you the answers in this one. The answer again is B. Okay. And just remember the proper time is measured on the slower moving clock, if you wish to look at it that way, or the one that's present at both events. So in one case, the proper time is on Peter's clock, and in the other case, it's on Sarah's clock. Oh, well, they've already got that. This is an explanation which I suggest you just read through quickly. This explains how we got to the answer. Okay. You'll be able to read all of this again on the YouTube video, well, not YouTube, but the video or whatever UCT does with the videos of these lectures at the end of the month. Okay. All right, I've got another one. I mentioned to you this one yesterday as well. It's a miniature spaceship. I've put the answers in. Flies past you horizontally at 99% the speed of light. Well, just rank the following distances from longest to shortest. Which one's the... yes, I might have put... You've got the printout is slightly different because there were 5, and that was an error, Francois. Well spotted. Perhaps I'll just go through then to the explanation, because you can see here what the answers are. That's a little bit longer, but if you read that, you'll hopefully get an understanding. Remember, if you would like copies of anything, hard copy, just send me an email and I can send it to you. So if you'd like a printout of this, I can email it to you. Okay, can I move on? This one I omitted to put up yesterday, but this is the one to challenge the doctors in the audience. And this is the ECG of a twin traveling in a spaceship in frame S prime at 99% the speed of light relative to twin B on Earth. Now, it's an identical twin, and when they left Earth, they were obviously the same age. They took an ECG monitor onto the spacecraft, and this is the trace that they got. Now, the identical twin happens to have an identical ECG. Now, that's not necessarily given, but in this case it is. So the twin on Earth will record their ECG on an identical ECG monitor to the one that the one in the spacecraft has got. And when the journey's over, they're going to take out their ECG traces and have a look at them and see what they are. This is a heart rate of about 60 beats a minute. What do you think the ECG of the twin on Earth is going to look like? Remember that The proper time is in the spacecraft. The time interval on Earth is different. Will the ECG look any different, or will it look the same? Who thinks it'll look different? There's one. Okay. On an absolute basis, they're going to cut the traveler in the spacecraft has taken the ECG monitor, the paperwork, the everything. They're going to get the printout, they're going to fold it away, and when they get back to Earth, they're going to pull it out. Same with the guy on Earth. Yeah. Well, here's the answer. No, the time in the spacecraft hasn't stopped. It's slowed down relative to the person on Earth. It's not slowed down relative to the person in the spacecraft. When they measure their heart rate, if they take a pulse and they measure it on their watch, they'll still get 60 beats a minute. All their bodily functions continue at the same rate. Okay. Go away. All right. So it would be no different. Because the point is, are we moving or aren't we moving? And we don't factor that in when we look at ECGs here. I chose an ECG just as a simple example because it could just as well have been the pulse rate. But what I would think on Earth, if it was traveling at the speed of that demonstration that I did yesterday, those heartbeats they wouldn't be 1 second apart, they would be 8 seconds apart as visually as observed on Earth. But that's relative reference frames. I'm talking about absolutes inside 2 different reference frames. Remember, the laws of physics are the same in every frame. You don't suddenly become some kind of a monster in the spacecraft. All right. I thought it might be useful just to recap quickly what we've learned so far. First thing is that all speeds are relative. It's very important. There isn't such a thing as absolute speed. You can only measure it relative to something. A reference frame is something that has 3 spatial coordinates and a time coordinate. And an inertial reference frame is one which is either stationary or moving at a fixed velocity. Or sometimes we can talk about constant speed in a fixed direction. And an event has an X, Y, and Z location and a time, but an instant in time. It's a 1 number. So 4 numbers define an event. It tells you when and where it had happened, such as the noon gun firing on Signal Hill every day. That is an event. You know exactly what time it happened, and you know exactly where it happened. The measurements are done with clocks and meter sticks and are present at the event. It's very important that within a particular frame, you have to have clocks and meter sticks present where the event takes place. Otherwise, you don't get the right answer. And the clocks all have to be synchronized. They need to be telling the same time. Events which are simultaneous in one reference frame may not be simultaneous in another. And I'm going to develop some more maths later on this morning where you can calculate what these differences are. Time dilation, observers observe clocks to be running slow that are moving relative to them to be running slow. And it doesn't matter whether it's a grandfather clock or a super accurate atomic clock. Any kind of clock gives you the same difference. Likewise with length contraction, if you took a ruler into a spacecraft flying near the speed of light to the observer in the spacecraft, nothing changes. But to an observer on Earth, they will see that ruler as having shortened. And this is a key one. Proper time is the time on a watch which is present at both of 2 events. So if something happens here and something happens there, the clock that happens to be here and there for both of them is measuring the proper time. The other observer would need 2 clocks to take the measurement, and that's the other observer's time. And likewise, a proper length is a fixed length which is present at both of 2 events. I hope that's what you have learned so far. Okay. I was asked the question yesterday, why can't light escape from a black hole? And I wasn't thinking clearly, but I went onto the internet last night and I got this graphical representation which tries to explain it. The print is not very clear, unfortunately. But what happens near a black hole is gravity is so strong, the gravitational field is so strong that it warps space-time so much that what happens at the event horizon is light falls into the event horizon and then gets trapped in there. It just goes round and round in circles. It's still traveling at the speed of light, but it can't get out because it's now got curved space-time. To the light beam, it's still traveling. It thinks it's still going in a straight line, but its straight line is something more. Think of a geodesic, or if you're coming up the curves of the Earth, you go round and round and round and round, thinking that you're just continuing in a straight line, but you never get out of the position that you're in. And it's not gravity that's slowing light down, it's gravity that's bending space-time. Okay. A gentleman asked me, how does this experiment illustrate the invariance of physical laws? One of the textbooks that I recommend that you have a look at is this one, University Physics. And if you go to pages 120, 1242, 1243, you get their view on the validity of that concept. But there's also free access to this website. It's a hell of a long web address. But I suppose if you put that in and do a Google search, you will find out. And you can see what the title says. Relativity wasn't Einstein's miracle. It was waiting in plain sight for 71 years, because Faraday discovered these things 71 years before Einstein actually codified it. Okay? I think that deals, that deals with the past. Okay, the next thing we're going to look at is Lorentz transforms. And where they become useful is if I've got this reference frame moving, this one moving relative to that one, you've got, as I mentioned in the first lecture, the coordinates that you will see in this frame, the x, y, and t prime coordinates and the time t prime coordinate, will be different to the ones that you have in this frame because they're moving relative to each other. The question then is, well, how do you do the calculation? How do you convert from one to the other? And I'll go through how that is done. And this is the sort of thing you need to do to resolve the twin paradox. If you try and think through it without doing some of the mathematics, it's very difficult to come up with the right answer. This is a very complex looking diagram, but essentially all that it's telling you is that if you've got this reference frame here, this is the S frame, and this is the S prime frame over here, you need to construct diagrams like that. And out of that, using some of the logic that we used when we were looking at the speed of light and things like that, you can come up with a set of equations. And I think I'm going to just jump to the equations because I'm not going to go through all the steps you need to take. They're not difficult equations. We'll come to, here they are. And what you find is it's this fairly simple relationship. X prime equals gamma x minus ut, and t prime equals gamma t minus ux over c squared. Now you'll notice something very interesting about this equation immediately. X, the space coordinate, is expressed in terms of time. And here the time coordinate is expressed in terms of x, the space coordinates. In other words, space and time are getting intertwined, and they are. When this value u gets big and approaches the speed of light, t prime and t become very different, and x prime and x become very different. That is one of the biggest conceptual leaps that Einstein made, is that space and time are actually interchangeable. And the way in which you do that changing is through moving at breakneck speed. But there it is. And you can use, these equations are, the Lorentz equations are the most useful equations one can use in solving relativistic problems. Lorentz was a Dutch physicist and a friend of Einstein's, and helped. Einstein often came up, he was a brilliant physicist, but he sometimes lacked the mathematical skills to solve problems, and this is one example where he got Lorentz to help him. Obviously, x and y and z don't change because neither y and z are moving relative to each other in the y and the z plane. We will later on come to something more complex where you do have three-dimensional movement, but the mathematics just gets a little bit more complex. Okay, so there it is. Those are the Lorentz transforms, probably the most powerful equations in special relativity. Okay, space and time have become intertwined, and we can no longer say that the length and time have absolute meanings independent of the frame of reference. I know I'm hammering this point home all the time, but that's what it is. If you don't have a frame of reference, it doesn't mean much at all. And the dimensions x, y, and z and t are called the space-time coordinates, or we just refer to it as space-time. There's another set of equations which unfortunately I won't be able to cover in these lectures, called the Minkowski equations. Another friend of Einstein's, he was I think a German mathematician, where he showed how you could relate these three things together as you can do with Pythagoras' theorem with spatial coordinates, but we sadly don't have time for that today. So we'll just stick to using the Lorentz transforms. Now, we've talked about things moving in a reference frame, this frame moving relative to that one. What we haven't considered yet is what happens if you have this frame. I'll take this one. It's moving relative to that one. Here we go. This is the x-axis here. I'm traveling in this frame, and now I fire this rocket. What speed are we going to register in that frame over there? It's clearly not going to be the same speed that you register in this frame. It's going to be a different speed as seen in that frame. And I stress this is just one-dimensional. It gets quite a lot more complex when you look at a three-dimensional event where this rocket ship is not traveling in the x direction, but perhaps is traveling in that direction. Or, yeah, how would those guys record the speed at what have you? It can be done. And again, the result without derivation is the following. You got v in x prime is vx minus u over 1 minus u vx over c squared. Not a difficult mathematical concept, but you can see there immediately that vx and v are not the same quantities. So if you wanted to solve for that, you just have to plug that into the equations, rearrange it, and you would get the answer. Now, another useful observation was when Vx equals c, in other words, when we're getting towards the speed of light, then you find that Vx prime, and not surprisingly, works out to c. And that's the mathematical equation that demonstrates it. So now I'm not just making a statement that the speed of light, you can't exceed the speed of light. There's mathematical evidence that you can't do it either. Okay? You can see, despite the somewhat complex looking nature of that equation, that is what it boils down to. Okay. You've understood that, so the velocities are different. I'm going to look at another example here. If we had a set of Russian dolls, and I'm assuming, I've used this as, just to illustrate it. This is a spacecraft, and it's going to leave, well, let's say it leaves in this frame. This is going to be fired into space at half the speed of light, and off it goes. While it's in flight, it's going to fire another missile. This missile is going to, or this rocket, is going to leave this one at half the speed of light, okay? So that one was at half. This one is now a half plus a half. Later on, this one then releases another rocket ship. Here we go. That one's traveling at half the speed of light, relative to the spacecraft that sent it off. Then the next one goes on. It fires off another rocket ship which is going at half the speed of light relative to this little guy. And so we go on. There's one more. I think, no, there are two more. Okay. And so you get it, all right? Each one of these little rocket ships were fired. This one was fired from Earth at 50% of the speed of light. This one was fired from that one at 50% the speed of light. This one was 50% of the speed of light, and again. So if you add them all together, you get about 2 or 3 times the speed of light by the time you get to this last rocket. Something's wrong. If you use the Lorentz velocity transforms, you get the right answer. And I'll show it to you on this slide. This is the velocity profile of the first rocket ship fired. You could choose to send it at any velocity relative to the speed of light, starting at 0, in which case it's not moving, or at the speed of light, in which case you are at a speed 1. So this is, obviously, if you're traveling at 1, then your speed on this axis, these are both relative velocities. This one's straightforward. It's obviously just a one-to-one relationship. Now, if I took another, so if I look at this one where we were looking at, if I took a rocket ship over here at 50% the speed of light, firing another rocket, you would expect the speed of the second rocket to end up there. But in fact, that's not what happens. That's what you get. Now, the way to read this graph is that at 30% the speed of light, I fired another rocket at 30%, and then it would be there. At 40% the speed of light, I fired this one at 40, and you end up there, and so on. And you'll see when you get to the speed of light, if you fire another one at the speed of light, you've still got the speed of light. So let's see what happens now. So we've got this one at 50%. I'm going to fire another rocket over there at 50%, the speed of light. And look what happens there. So now you've gone from there to there. You still haven't got to the speed of light, although these three are all traveling at half the speed of light relative to each other. This guy relative to Earth, this guy relative to this guy, and that guy relative to that guy. Then I'll fire another rocket, and another rocket, and another rocket. And what you notice is that you never ever get past the speed of light. Somebody on Earth looking at these rockets flying will see them flying at one of these speeds. If they all went off at 40% relative to each other, the first rocket would be at that speed, the second and the third and the fourth and so on. This is where relativity really can play with the mind. So no matter how many rockets you fire, whatever speed you choose to fire them relative to each other, you still end up never being able to get past the speed of light. And if you use the Lorentz velocity transforms, that's how I got those graphs up on the board there. Silence. Any questions? It's a fascinating fact that you cannot break that law of physics. Okay, I'll move on.
So just one thing. If, for instance, you are on the, shall we say, the third rocket that was fired,
Yeah.
in that position, you will then see the other rockets traveling at the speed you fired them at.
Yeah, correct. Yeah, so take the first rocket. If he's flying at 50% the speed of light. The rocket that's over here, relative to him, is flying at the 50% the speed of light. So the observer on this rocket ship here will see, the observer on this rocket ship will see a straight line like this one here, because this is what the observer on Earth is going to see. They'll all see the straight lines, but that'll be measured relative to their velocity. And it sounds crazy because each one's relative to each other one's going half the speed of light, yet nobody ever exceeds the speed of light. Okay, move on. I'll take you the next thing, which is the last area of special relativity I'm going to go into before we go into particle physics, and that's to look at the relativistic Doppler effect. I need to say straight away, the Doppler effect with electromagnetic waves is completely different to the one that you have with sound waves, because with sound waves, the velocity depends on the speed of the medium that the sound wave is in light, and electromagnetic waves, the medium doesn't play a role. So we go with another thought experiment with a high-speed train, and here we have it. We have a train moving along here at speed u. There's Stanley in frame S, observing the train coming towards him. Again, this is a train very near the speed of light. It emits a light pulse or an electromagnetic pulse over here. You call it light at frequency f0. When the train reaches this point, a second wave is emitted there, and this is the position of the first wave relative to the second wave over there. So you can see what's starting to happen. Okay. So what actually happens is that Stanley starts to receive waves at a greater frequency where f is greater than f0, because the interval between the waves arriving at Stanley has been shortened. The wavelength has been shortened, so the frequency has gone up. The speed of light hasn't changed. The speed at which this light is traveling is the same. But if you think of the light coming along as a sine wave, all that you are doing is you're shortening the time between the peaks of the wave reaching him here. And if you increase the frequency, you're going to move the color towards the blue end of the spectrum. If you start at red, you're going to move to blue. Or you start anywhere below. You can start with radio waves. If you accelerate them enough, eventually they'll become blue. And that's because the actual peaks of the sine wave arriving at the observer are getting squashed up closer and closer to each other. It's another one that you can play tricks with your mind. How does this happen? Because the speed of light hasn't changed. Okay, and there's a simple formula that you can derive. F is equal to C plus U over C minus U square root of times F naught. And that gives you the blue shift. Okay, as you approach the speed of light. Of course, if you got near to the speed of light, all of these waves here would be gamma rays. Or I don't know whether there's something that comes after gamma rays, but it's that end of the spectrum. So you could make the waves pretty dangerous just by coming at you very fast. Okay, so as I mentioned, light and sound are not the same. It's the relative velocity of the two that determines what you're going to see. And here's a graph of what it looks like. If you start off with your relative speed equal to 0, it's stationary, and take it up to 1, which is the speed of light, the frequency, the blue shift this is f over f naught, looks just like the gamma function, and it goes all the way up there to infinity. So if this was a radio wave, and you went up to here, that you might be in the light area there, or infrared light, ultraviolet, X-rays, gamma rays, whatever. And that's how it works. And it comes again from Einstein's and Lorentz's equations. Yeah. Yes. Mm-hmm. You've changed the energy of the photons, because as the frequency gets higher, the energy of the photon gets higher in your reference frame, not in the reference frame of where it came from. That's also a tricky one. You could have two. Another way of looking at it: if you have two inertial reference frames and two bodies, neither of which is moving in the frame. Yeah, you could have a stationary guy, and here's another stationary guy. But these two frames are moving towards each other. They're inertial frames. Neither of those two bodies have got any kinetic energy, but boy, when those two frames meet, you will find they have kinetic energy, because relative to the other frame, it has got energy, but not in its own frame. And that's also quite I'm glad you asked that question, Annie, because it's difficult to get your head around. People always say, where's the energy gone? It's not lost. It's that you're looking at it in a different reference frame. Or it's not gained. You're not getting something for nothing. Sorry? No. We'll come to nuclear power later in the lecture. Yeah, no, it's a different principle. Okay. It's possible that in a hydrogen bomb, the explosion is so powerful that the particles, solid particles, particles of matter are ejected at near the speed of light, and then things would happen. But I don't even think a hydrogen bomb would do that. I don't know. All right. So what happens if the source is moving away from the observer? You're going to get longer wavelengths. They're going to stretch. And this is Doppler redshift. And that's the formula, C minus U over C plus U times F naught. Now, the one question, that's it. It gets short. Yeah. Gamma's disappeared from these equations. You might say to me, but what's happened? And the reason is it's cancelled out in the derivation. You might say, well, therefore you don't need it. I promise you, if you don't start with the right Lorentz equations, you will never get the equations I put up on the board. They just happen to cancel each other out. The formula looks a little bit like the Doppler formula for sound, but it's not the same. I haven't got the sound formula there, but if you'd like to, you can check and see you don't get quite the same structure. And this is what that function looks like plotted as, again, as a function of your speed relative to the speed of light, starting at a ratio of 1 and ending up at 0. So if something moves away from you really very fast, it might start with as being an ultraviolet object, and eventually it'll just be radio waves. And you can see why astronomers need things like radio astronomy and the likes, because with stars moving away so fast from us, that's where the frequency of their light actually ends up reaching us. Don't let the maths bother you too much. Try and remember the shape of the curves, and you can form an image more easily, I think, that way than bothering too much about the mathematics. Here's an example taken by the Hubble Space Telescope. This is a high-velocity jet being ejected from a black hole at the center of this galaxy, and you can see the light is quite blue. It starts off over there as being a whitish yellow light and ends up being blue. So that is a big explosion which is ejecting material at a phenomenally high rate, and its color changes as a consequence of that.
So to take this image, that's an actual image?
Yeah.
Right. But to see it, wouldn't you have to be seeing it, or wouldn't the picture have to be taken head on, as opposed to, it seems like it's been taken laterally.
It's actually coming at a slight angle, isn't it? Let me think. If it went across, it's not entirely head-on. I mean, the Hubble Space Telescope is probably down here, so... Yeah, so this is the angular velocity, yeah. But it would still give you that, unless it was perhaps at right angles, in which case you would notice it. You're right. That's a good point. No. It's just that the particles that are coming out, they're very hot. They are white light. They're traveling so fast that as we see it, we see the blue light. No, it does expel particles. Black holes do. No, they do expel stuff. Yeah, that's what that is. Yes. Yeah, that's a black hole letting some of the stuff go back again. I should write a letter to Hubble. I don't know. The black holes do emit matter. That they've discovered in the recent past. Okay, radar makes use of this Doppler effect. Here's an example. This is on the Queen Mary. There are quite a few radar antennae there. So it does have use to man. Obviously, airports make a lot of use of radar. And this guy's not so friendly, but he's trapping you. Interestingly, with radar, if a car's coming towards him, you get a double Doppler effect, because you send the signal out, it bounces off an object moving towards you, that then re-emits it back to you, but it's moving relative to you, so you get twice the frequency shift that you would do if you were just moving, if he was just measuring a moving particle coming past. And this is a development car by one of Uber's cars, which is using LiDAR technology, where they're using light to do something similar to radar. And it's all part of the intelligent systems that they're building into driverless cars, because it's got to recognize things like trees, grass verges, pavements, white lines, cyclists, other motor cars, etc., etc. And it needs all sorts of, so they'll use radar, but they'll use LiDAR as well, and LiDAR is just the light equivalent of radar. All right, that brings us to the end of standard special relativity. I'm going to take you on to relativistic particle physics, because now we start to talk with things that really are moving near the speed of light. And we'll start looking at what the energies and what have you of these particles are. But before I go, are there any other questions perhaps before I move on? Okay. The first thing to consider is relativistic particle momentum. Newton's laws of motion have the same form in all inertial reference frames, but using Lorentz transforms to change from one frame to another, the laws should be invariant. In other words, they shouldn't change. And the principle of conservation of momentum states that when two bodies interact, the total momentum is constant, providing that there is no external force acting on the bodies. That's old physics. I think we can all agree with that. So conservation of momentum must therefore be valid in all inertial frames of reference. But as you've just seen, that when you do the Lorentz transforms, velocities and what have you change? So how can the momentum be retained? So if we look at a collision between an inertial coordinate system, we find that the momentum is conserved, but we need to use, when we look in a standard frame S, momentum is always conserved. But when we get to the Lorentz transforms and we apply it to that, it will tell you no, the momentum isn't conserved because the velocity has changed. The mass hasn't changed, but the velocity has. So what is wrong? We're not conserving momentum. And that is because that P equals mv equation there turns out not to be correct in a relativistic environment. So we need a different definition of momentum in relativistic terms. And this is the equation that you need. In a relativistic environment, momentum is equal to mv over the square root of 1 minus v over c squared, which is gamma mv. And you'll immediately see, remember what I said yesterday, where that's in the numerator, this thing's going to tend off towards infinity. So in relativistic physics, the momentum is defined by that equation. You can derive that actually from first principles, which is in one of these worked examples that I've got in front here, but it's quite a few pages of maths you need to get there, and I'm not going to do it. But just keep that in mind. So relativistic momentum is greater than it would be in the S reference frame. And this is absolutely key to understanding the kinematics of particle physics. When you've got particles moving near the speed of light, as you do in colliders and accelerators, you have to take the relativistic effects into account. What we will use, instead of U, we're going to use V for the particle physics, for the particle speed. And the reference frames we're going to assume we're in the particle's reference frame. So we don't need to be comparing one reference frame with another all the time. And this is the actual graphical representation of what happens to momentum. This is, again, your speed relative to the speed of light. And you'll see what happens. Remember, gamma is in the numerator, and the momentum, as you approach the speed of light, goes off to infinity. Now, a point I'd like to make here is, while all of this is happening, the mass of the particle has not changed. It's still m. It's on the scale here. M is a constant. M and c here are both constants. But the momentum becomes infinite when you get up here. So something with a very little mass has got infinite momentum, and that led physicists in the early days to wrongly state that the particle mass has increased. The particle mass has not increased. It will get to an infinite momentum without any change in mass. If we look what the Newtonian mechanics tells us would happen, well, in that case, momentum would just be equal to mv, and it would be this red straight line. And the only way you could ever get this line to go to infinity is if this went off to infinity here. And that's not going to happen. So that's quite profound. Yeah, the momentum goes careering off to infinity. Okay. So what does this do to force and acceleration? Force, in simplistic terms, is equal to mass times acceleration. In the middle, there's a derivative for those who understand derivatives. It's the rate of change of momentum with time. And without a lot of derivation, this is what relativistic force looks like. If you are applying a force and accelerating a particle at very high speed, you need to use this formula, which has got gamma cubed m times acceleration. So you can see that that's going to scream off to infinity very, very quickly. So as you try and accelerate a particle or change, in other words, change its momentum, the amount of force required becomes absolutely enormous as you approach the speed of light. But by rearranging that previous equation, I can express it in terms of acceleration. And I find this actually a more useful formula to consider. Acceleration is equal to this guy here. Now you see that the gamma cube is in the denominator, so that's going to rapidly drop off to zero. So what actually happens is, if you apply a constant force to a constant mass, A will drop to zero. So you can't accelerate it, even though you've got masses of force to do so. Of course, I'm talking about the force, the mass and the acceleration and the force all in the same direction. If they're at right angles to each other, you need different physics to work out what the resultant will be. Okay, as it accelerates, as the speed of a particle picks up, the acceleration decreases as you approach the speed of light. And as I've mentioned, you can't do anything about it. And this is illustrated in this slide here. If you take that equation that I showed you earlier on, here we go again. We start with the particle at rest, and we're going to accelerate it up to the speed of light. This will be your acceleration. This is a force over mass. This is a constant all the way up. And once again, I'm not changing the mass of the particle, but the acceleration screams down to zero. So when you get to this point, it doesn't matter how big f is, that number will be zero. Yet again stating you can't go faster than the speed of light. The physics keeps coming back to the same answers. Yes, sir?
I don't understand how the force is constant.
Sorry?
I don't understand how the force is constant.
Well, you keep it constant. If you took a constant force in Newtonian mechanics, and you applied it to a body of constant mass, it will accelerate forever. It will keep going faster and faster and faster and faster and faster. But when you approach the speed of light, in relativistic terms, it doesn't matter how much extra force you put in, it won't accelerate anymore. The acceleration will decrease. Have I answered the... Yeah. Okay, I don't think I have the... Did everybody else understand that? That the difference with... Typically, if you apply a fixed force to a fixed mass, it'll keep going faster and faster forever until you take the force away. And then it'll continue, incidentally, at a fixed speed. It won't change after that. But in relativistic terms, you won't actually get there because the amount of force required to accelerate becomes infinite. So once again, it's not the mass that's become infinite. If we had infinite mass, then you'd have infinity squared over here. I suppose it's possible, but yeah. All right. Maybe quickly move on to relativistic work and energy. For those who can remember their physics, the kinetic energy of a particle equals the work done on moving it from rest to speed v. And this is the equation for kinetic energy in relativistic terms. Kinetic energy there equals gamma minus 1 mc squared. And that's it. This is not difficult arithmetic, but that's the shorthand. That's effective. I've skipped a few steps in the derivation because I really want you just to focus on the fact that k equals that quantity over there, and then we'll see what it looks like on a chart. So as v approaches the speed of light, k approaches infinity. But in Newtonian terms, k can only become infinite if v is infinite. And here we have the kinetic energy chart. We take our particle from rest up to the speed of light, and there's what happens to the kinetic energy. You can see this is a very steep curve up here. Again, mass is kept constant throughout this chart. Here's what it would look like if kinetic energy is equal to half mv squared in Newtonian terms, and that red line there illustrates what Newtonian mechanics would illustrate. So when Newton was doing his work, he was only working in this region, and his equations all worked down here. But had he been looking at stuff up here towards 20-30% the speed of light, he would have found that there were errors in his formula, or his incomplete formula. All right? So let's have a look how we relate all of this to each other. There's a thing called the total particle energy. A rest energy equals mc squared. You all recognize that equation. And massless energy. And something we're going to learn is that massless particles have both momentum and energy. Yet in classical terms, momentum is m times v, and if v is naught, the momentum should be naught. It's not. So let's just recall the relativistic kinetic energy can be expressed in these two terms. And if you look at them, that's the equation I showed you just a minute ago. You've got a motion term here, there's the velocity there, but then there's this term here that's got no motion in it at all. It's only got mass, and c is a constant. So the kinetic energy of a particle actually depends on both its velocity and its mass. Okay, the motion term depends on motion, and the rest energy is independent of motion. So what it looks like is that the total energy of a particle, well, rather the kinetic energy is the difference between the total energy and an energy mc squared that it has even at rest. And this is how you can express it. The total energy of a particle equals the kinetic energy plus the rest energy, which is it derives from its mass, and that's gamma mc squared.